Okay, I wanted to do this example using cylindrical, or in this case it's two-dimensional, so we could just call it polar coordinates. We won't have a z acceleration to worry about. But we have this particle, and it's going around this curve, and the radius is a function of theta. So it's changing as the angle sweeps, in this case from the y-axis here. So at 0, it's straight up, okay? Theta 0 equals 0, which is straight up. We do have a velocity. Angular velocity here is also a function of time. So as time goes on, this is going to sweep a lot faster. Okay, it's going to pick up a lot because t squared is going to really accelerate that angular velocity. So we have r is given in meters. We have angular velocity in radians per second. And they want to know the velocity and acceleration. So we want to find v at 30 degrees and acceleration at 30 degrees. And these could be the vector at that point. Since they don't ask for the magnitude, we could leave it in vector form, but we'll also find the magnitude of these, which that would be really hard to find without this principle. So we want to find those. To do that, we know in our equations we're going to need r dot, so the velocity and acceleration in the radial direction. We're also going to need theta dot, and theta dot. So we have a function here, so we can find all those, and then we'll plug them in our velocity and acceleration equations, and we'll be done. So if we start off with r, that's a more complex function here. Our radius is 5 cosine of 2 theta. Okay, and at 30 degrees, 5 cosine of 60 degrees. We can use degrees here. We're gonna take the cosine or sine of those anyway, so that'll become a decimal. So r at 30 degrees equals 2.5 meters. Okay, got one already. Easy so far. Now r dot, which equals dr dt. Problem. Because we have r as a function of theta, not a function of time. So what we're going to have to do is take dr d theta using our chain rule times d theta dt, okay, to give us dr dt. So our r dot equals the derivative of our function here, 5 cosine of 2 theta, in terms of theta, is going to be derivative of cosine is negative sine, so we're going to have negative 5 sine of 2 theta times the derivative of the inside, which is 2. All right, now that is the dr d theta part. What we also have to do is multiply that by d theta dt, which is theta dot, which is, we know, we don't know. We know it in terms of time, but we don't know how much time it takes to get to 30 degrees. So we need to find theta dot before we go any farther. And we can go ahead and simplify this a little bit. I get negative 10 sine of 2 theta times theta dot, or d theta dt. Okay, so we got to stop there. We can't go further until we know what theta dot is. So, well, we could go on and find this in terms of theta dot. But we can't actually find the value yet. So let's go on and find, while we're here, our dot dot is the derivative of this, and we have two variables here, this one and this one. So we have to use our product rule. So I'm going to take the derivative of negative 10 sine of 2 theta with respect to dt. We can't take that with respect to time. So we're going to take it with respect to theta, and then we have to go d theta dt to actually take the derivative of this first part. And we have to bring this down. So we have theta dot. So I take the derivative of this first part times this. That is all the derivative of the first part. Then I take this times the derivative of the second. So then I actually have a negative 10 sine of 2 theta. Derivative of theta dot is theta dot dot, or the second derivative of theta with respect to time. Right, so I have r dot dot. Derivative of negative 10 sine of 2 theta is going to be negative, well, let me do it in process here, 10 cosine of 2 theta. Then I have to take the derivative of this part, which is 2, times d theta dt and d theta dt. So I get theta dot minus 10 sine of 2 theta, theta dot dot. So you can see why we came up with this dot notation. When I say we, I mean they, because writing a lot of dt's would be kind of complex. Okay, so we can simplify this. R dot dot equals negative 20 cosine of 2 theta, theta dot, we can just say squared. When we find that number, we'll just plug it in and square it. Minus 10 sine of 2 theta, theta dot dot. Okay, we can't find this till we find theta dot and theta dot dot. So let's go up here and work on that. All right, so now we're working on theta. Our function of theta, we don't know what theta is. We need to find that, but what we have is theta dot equals 3t squared. So to get theta, we need the integral of theta dot with respect to time, which equals from 0 to t, 3t squared dt. So when we integrate that, it's pretty easy, right? Theta equals t cubed from 0 to t, so that's just t minus 0. So theta equals t cubed. So if we want to know what theta is at time equals 30 seconds, or sorry, when time, we want to find time when theta equals 30 degrees, we're going to plug in, we can't take a cube root of 30 degrees. Degrees doesn't work that way. So we're going to convert 30 degrees to radians. So we take 180 degrees and pi. Okay, so at theta equals 30 degrees, which equals 0.5236. Just did that in my head. Kidding. Radians. Okay, so then at 0.5236 radians, we take the cube root of both sides. We find out that time equals 0.806 seconds at theta equals 0.5236 radians. All right, now that's important. We know how long it takes to get there. That's cool. Now we can plug that in and find out theta dot which equals 3t squared, which equals at theta equals 30. Make that better. Theta equals 30. 3 times 0.5236 squared. All right, so that's easy to calculate. Theta dot at 30 degrees equals 1.949 radians per second. Cool. Now we can plug that in over here and find out at 30 degrees r dot equals sine of 2 times 30, which is 60, sine of 60 times 10 times 1.949 r 30. The rate of change of the radius at 30 degrees is going to be negative 16.88 meters per second. That's another important number, so I'm going to put a little triangle. It's not the answer. Don't want to box it, but we'll need that to get the answer. All right, let's bounce over here, because the other thing we need is theta dot dot. So we have the function 3t squared. How do I get theta dot dot, which equals the second derivative of theta dot, or of theta. Of course, that is just going to be 6t, the derivative of theta dot with respect to time. So we can solve this where t equals, what was the time? 0.806 seconds. So theta dot dot equals 6 times 0.806, which equals 4.836 radians per second squared. Okay, though these numbers are important. Okay, but now I have I've got r dot dot, theta dot, theta dot dot. So now it's just plug and chug to get my velocity and my acceleration. So let's start with velocity equals r dot. Here's my equation off my crib sheet, plus r theta dot in the theta direction. Okay, now you plug numbers in. My r dot is negative 16.88. And the r direction, plus my r, which is 2.5 meters, in the theta dot direction, theta direction, but I need a theta dot in here first, which is my 1.949. So my velocity equals negative 16.88 in the radial direction, and plus 4.8725 in the transverse direction, or theta direction. And that's my vector answer for velocity. But now I can find my magnitude, which equals the square root of velocity in the radial direction plus velocity in the theta direction. Equals the square root of 16.88. Put the negative sign if you want to, plus 4.873 squared. So my velocity equals 17.6 meters per second. Right? Cool. That's at 30 degrees. So that means up here, my velocity is going 17.6 meters per second at that point at theta equals 30. Cool. Now the acceleration, a little more complex here, but we have all the numbers we need. We've got our r dot dot, double derivative of r minus r theta dot squared, and that's in the radial direction, plus r theta dot dot plus 2r dot theta dot in the theta direction. We don't have to worry about z because it's a polar problem. There's no 3 dimensions here. So we just plug these numbers in. My r dot dot is, I haven't found that yet, have I? Let's zip back up here. R dot dot at 30 is going to be, plug in 30 degrees, negative 79.9 meters per second squared. All right, so we're going to plug in 30 degrees for theta. We're going to plug in 1.949 for theta dot, and for theta dot dot, we're going to plug in 4.836 into this equation and find R30, R dot dot. Okay, which comes down here, negative 79.9 meters per second squared, minus R, which is 2.5 times 1.949 squared. That's all in my R direction, plus R 2.5 again, theta dot dot 4.836 plus 2 R dot, which we found to be negative 16.88 times theta dot. It's easy. That's why I put these little triangles here. It's easy to lose track of things. R dot, theta dot. And that is all in my transverse direction. So my acceleration, I can punch these numbers out here, find out that this is negative 89.4 UR, radial direction, minus 53.7 in the theta direction. Wow. And find my magnitude here is going to be 89.4 squared plus negative 53.7 squared, which if I did all my numbers right, it's going to come out to 104 meters per second squared. Okay, that equals a. So again, it kind of seems complex when you look at the whole thing, but it's really just find those first derivative and second derivative of the radial, and the first derivative and second derivative of theta function, and then plug them in the equations, and amazingly, we can determine the velocity here and the direction. So it's actually negative. It's accelerating this way in the r direction, I should say. This way in the r direction, and in the theta direction, slowing up. It's going backward. Okay, so that's my acceleration theta, acceleration r.